Greetings everybody, and welcome back to another ring theory video. So now that we have some basic understanding of rings, we want to start building towards the quotient ring, which is a very important construction. We're going to see it again in the first isomorphism theorem, which is a very important theorem, and we're going to see it in modules as well, and we're going to see it used in constructing field extensions. So it's a very important construction, and the first step to understanding the quotient ring are taking a look at these so-called ideals. Now, to understand the motivation behind the ideals, we're going to take a look at some group theory, so we're going to review some of that. First of all, we're going to let R with addition and multiplication be a ring. Then we know by the definitions that R with addition is an abelian group. So let's remember how we can construct quotient groups in group theory. So we're going to start off with a group which is a set. In this case it's going to be R, and we have some composition operation, which in this case is addition on the ring. So R with addition, this is an abelian group. And for illustrative purposes, let's say the identity of this group is over here. The identity of this group is going to be the additive identity of the ring, which is just the zero elements. What we're going to do is we're going to consider a subgroup of R with addition. Let's call that I. And the nice thing about this subgroup is that it's a normal subgroup. And that's because R was an abelian group to start with. And if you have a normal subgroup, then you can construct the quotient group as follows. What you're going to do is you're going to pick some elements outside of your subgroup, let's call it A1, and you're going to add it with every single element inside of the subgroup I. And you can show that this generates a brand new subset of your original group that's completely disjoint. The group operation here is addition, so we commonly denotes this coset here by A1, which is the elements that's generating this coset, plus I. In general, that plus there would be the group operation that you've defined. So these guys are cosets. And you can repeat this construction each time picking a brand new element that's not already in the cosets that you already have, and adding it to every single element in I, and that gives you a completely new disjoint subset. And you repeat this construction until you fill up your entire group. Once we have all these cosets, we're going to collect them all together, and that's going to form the quotient group. It's essentially a partition of your original group. You're dividing it up into each of these disjoint subsets, and you're treating each of those subsets as elements. We write the quotient group as R mod I. This is defined to be the set of all A plus I, where A is in R. This guy is an abelian group. And from group theory, we also know how to define the composition on this quotient group. Namely, if you take two subsets, A plus I, and you add it with another coset, B plus I, then this is going to give you the cosets A plus B plus I. So far, this quotient group, it's a group, but we also want to inherit the ring structure from our original ring onto this quotient group as well. The question is, do we need to impose any extra conditions on this normal subgroup over here? Because this set I here, that's just a subgroup at the moment. And it's only concerned about this addition operation here. Do we need any extra conditions on the multiplication operation in order to have somewhat of a similar structure here for multiplication? Ideally, no pun intended, if you have two cosets and you try to multiply them together, let's say A plus I and then B plus I, you would like this to give you A times B plus I. Let's try to understand this equation a little better to see if we need to add any extra conditions on our subgroup I. Let's just choose some element of each of these cosets we're working with here. So for example, on the left hand side, an element of the coset A plus I would look something like A plus I1 for instance, and an element of the coset B plus I would look like B plus I2 for instance, where I1 and I2 are elements of I. And on the right hand side, we need this to be equal to AB plus some elements of I, let's say I3. Let's expand out that left hand side there, and we're going to get A times B plus AI2 plus I1B plus I1I2. And this is going to be AB plus I3. These ABs here are going to cancel. And essentially what we're left with is that this left-hand side is equal to some elements in your subgroup I. Or alternatively, we can just write this as AI2 plus I1B plus I1I2 is an element of I yet again. But I over here is a subgroup under addition, which means in order for this expression here to be inside of this subgroup I, each of these terms must be already in I, because addition is closed inside of I. So we require that A times I2 is in I1 times B is in I, and I1 times I2 is also in I. But notice A and B, these are just some random elements in your ring R over here that you can choose, which means in order for this equation here to make sense, we require that if you take any element in your subgroup I here and you multiply it with any element in your ring, it should give you back an element in your subgroup I. And if we impose this condition where multiplication by any ring element by an element in your subgroup I gives you back another element in your subgroup I, then this third condition over here also follows, because while I1 and I2, these are also elements of your ring R. Okay, so this subset I that we want over here, it's a subgroup under addition, but it also needs to satisfy one important property for the multiplication, which we just discussed over here. And if it satisfies that particular property, we can define such a multiplication on our quotients group, which is going to make it into a quotient ring. The question of whether or not this is well defined, we'll leave that to when we explicitly construct the quotients ring. But for now, when we try to construct the quotients ring, the thing we're modding by is not a subring, it's actually something called an ideal, which is a subgroup, it's an abelian subgroup, and it also satisfies that specific multiplication property that we just discussed. So this leads us to the definition of an ideal. An ideal, I, of a ring R, is a non-empty subset I in R such that the following hold. First of all, for all A, B inside of the subset I, it must be that A plus B is also in I, so it's closed under addition. Second of all, for all A in your ideal I, and R inside of your ring, it holds that R times A is inside of the subset I. And that's precisely the definition of an ideal. Now you might worry that an ideal is supposed to be a subgroup under addition, isn't it? But I've only stated one of these axioms over here for the addition, namely the closure property. Now associativity also follows as well because it's a subset, but how about the fact that there's a neutral element as well as there being an inverse? Well, we can give that as a proposition, and it's fairly simple to prove. Let I, subset R, be an ideal. Then we have the following. First of all is the neutral element property for subgroups, namely 0 is an element of I. And second of all is the inverse property, namely that for every single element A in your ideal I, you can find the additive inverse, negative A, also in I. So let's give a proof of that. It's very straightforward. First of all, let's choose some element A inside of your ideal. Then we know that inside of your ring R, the additive identity is in there, and also the additive inverse of the multiplicative identity, so -1, is also in there as well. And all we have to do now is use the second property for ideals, namely, if you multiply any elements of your ring R with any elements of your ideal, it should also give you back another element of the ideal. So that means 0 times A, which is 0, has to be inside of the ideal, and a -1 times A, which is negative A, we've proved that in the second video, that also has to be inside of your ideal I. So just assuming these two conditions over here is enough to ensure that I is also a subgroup under addition. Now what's an example of an ideal? Well, an excellent example is the kernel of a ring homomorphism. So let's make that a proposition. Let phi from R to S be a ring homomorphism, then the kernel of the ring homomorphism is an ideal. I believe I mentioned this in one of the previous videos. The kernel of a ring homomorphism is not a subring. Instead, it's something called an ideal. And we've just defined that, so let's give a proof of this. We just simply need to check those two conditions. First of all, we're going to let A and B be inside of this kernel. And we want to show that the sum is also inside of the kernel as well. So what does it mean for two elements to be inside of the kernel? It means that phi of A is equal to 0, and also phi of B is equal to 0. So let's add these two guys together, then we get phi of A plus phi of B is equal to 0 plus 0, well, that's a 0. But now using the ring homomorphism property, we can bring these two phi's here together, and that's going to give us a phi of A plus B, that's equal to 0. But this tells us that A plus B must be inside of the kernel to begin with. So that was the first property. Now we have to check the second property, which means we pick any elements of the kernel and any elements of the base ring, and we show that the product is also inside of the kernel. So we're going to choose some R inside of the ring R, and the reason why is, well, because remember the kernel of phi is a subset of the ring R, which is this domain ring here. Now what we want to show is A times R is inside of the kernel. So to do that, let's apply phi to A times R. Now, because phi is a ring homomorphism, we can split this up as follows. Phi of A and then phi of R but we assume that A was inside of the kernel of phi, which means this gets mapped to 0, and then we have phi over R. Now this is the 0 inside of the ring S, and this is the multiplication inside of S, so this is going to give us the 0 in S. So we found that phi of A times R gives us the 0 in S, which means that A times R is inside of the kernel of phi. Some other examples of ideals, if you take a look at the integers, you could have 2z, 3z, and in general nz, these are ideals. And as an exercise, you can show that if you have two ideals of a ring, then the intersection is also an ideal, and the sum of the two ideals, which is defined as follows, I plus j, is equal to the sets of all elements I plus j, where I is in I and j is in j. This is also an ideal. So that's all for this video on ideals, just a bit of a motivation as to where the definition comes from, because we're going to be using ideals to construct quotient rings later. So in the next video, we're going to take another look at ideals again, in particular principal ideals, which are a special type of ideals. And once we have that, we're ready to take a look at quotient rings as well as the first isomorphism theorem. So there's a lot of cool things coming up. Hope you guys enjoyed this video, and I'll see everyone in the next one.